Hey, last chapter. This chapter deals with protein metabolism, and we always start off with the digestion. So you ate some protein-rich foods. What's happening to that protein? How do you digest it? And then how do you metabolize it? All right, mouth. Nothing happens to the protein in the mouth. So you're just chewing, and then it goes into the stomach. In the stomach, several things happen. The minute you consume protein, this hormone called gastrin gets released, and gastrin activates the release of hydrochloric acid from the gastric mucosa, the cells of the lining of the stomach. That hydrochloric acid keeps the pH of the stomach low in the around 1.5 range. The HCl, hydrochloric acid, in the stomach has several key functions. So I have them written over here for you. Number one, it kills bacteria. So cool. Doesn't mean you should be consuming tons of bacteria, but just in case you are in your food, it kills the bacteria. Number two, it denatures the protein. And you already remember that from the protein chapter. If you throw a protein in acid, you lower the pH like crazy, what's going to happen? All the ionic bonds start breaking, and so all that tertiary structure changes, and so your protein begins to unravel. And when it unravels and opens up, now the protease enzymes, the enzymes have access to begin to hydrolyze the peptide bonds. The key protease enzyme in the stomach is an enzyme called pepsin, but it's released as pepsinogen. And pepsinogen is activated by hydrochloric acid. So that's the third function of the hydrochloric acid, is that it activates pepsinogen and then turns it into pepsin, and then pepsin can do its thing and hydrolyze peptide bonds. You're only going to hydrolyze about 10% of all the peptide bonds in whatever dietary protein you consume. So the rest of the hydrolysis of the peptide bonds occurs in the small intestine. Okay, so now everything leaves the stomach and goes into the small intestine. Remember, pH of all of this is pretty high, so we need to neutralize all of this. The pancreas produces bicarbonate ion. The bicarbonate ion brings the pH back up again. And now the enzymes of the small intestine are able to function at that the 7 point whatever. It's a bit basic. It's higher than 7 pH. Pepsin functions great at 1.5 pH, but the enzymes in the small intestine that finish the hydrolysis of all the peptide bonds are the enzyme trypsin, chymotrypsin, and carboxypeptidase. So these are the enzymes down here, if you can see them: trypsin, chymotrypsin, carboxypeptidases. Okay, so these enzymes are going to finish the whole hydrolysis. All the peptide bonds have been hydrolyzed. What do we have now? We have lots and lots and lots and lots of amino acids, and we call this the amino acid pool. So all these amino acids are going to go through the villi to the bloodstream, and now what are we going to do with all these amino acids? Let's talk about the fate of the amino acids. Or we'll say, what becomes of this amino acid pool? Let's write this down. Amino acid pool. All right, thousands and thousands and thousands of free amino acids are here now. What are we going to do with them? Well, 75% of all the amino acids in dietary protein are used to synthesize new proteins in the body. So number one, 75% are used for synthesis of new proteins. Do you guys remember back in the nucleic acid chapter when we said that translation, each tRNA is coming with a specific amino acid, and the anticodon of the tRNA comes and binds with the codon of the mRNA? Well, where do you think those tRNAs are getting all those amino acids from? Dietary protein, dietary amino acid pool. So 75% of all the protein you consume, all those amino acids are there for your tRNAs to come and put the amino acids in the right spots and create all the proteins that your body needs. Number 2, the synthesis of non-protein nitrogen containing compounds. Think about this. We've been doing biochemistry for a while now. Have we come across some nitrogen containing compounds that are not amino acids and not proteins? Think. Remember the purines? Remember the pyrimidines? Adenine, guanine, cytosine, thymine, uracil. All of those are nitrogen containing non-protein substances. Do you remember the structure of lecithin? Remember how we had that molecule choline as part of the structure of lecithin? Choline had a nitrogen in it. It wasn't a protein. So these are examples of non-protein nitrogen containing compounds. So part of the amino acids that you're consuming are used to make those. Okay, number 3, the synthesis of non-essential amino acids. Your book, this chapter, has a list of the essential amino acids and the list of the non-essential. The word essential doesn't mean important. The word essential just means your body can't synthesize it. So the essential amino acids you have to consume in your diet. And your body, what it can do is it can take those essential amino acids and use them to help make the non-essential amino acids. Non-essential amino acids are the amino acids your body knows how to synthesize, okay? And again, you can look at your book and see the list of each. And then number 4, and the way your body, not your body, sorry, the way your book approaches this is basically, it tells you that energy, you can use your proteins for energy if you want to, if you need to. You can't store protein. So once you've used all the amino acids to do everything you need to do, if there's an excess, so like if you're gigadosing on proteins or taking a ton of amino acid supplements, what is your body going to do with all those extra amino acids? If it doesn't need them to build new proteins and it doesn't need them to make any non-essential amino acids or non-protein nitrogen containing compounds, what does it do? Well, it deaminates the amino acids. It removes the amine from the amino acid, and then it can get rid of the nitrogen through something called the urea cycle, which we'll get into. And then it can use the carbon skeleton to do other things. So basically, there are some amino acids, the carbon skeleton can get turned into pyruvate. And some amino acids, carbon skeleton can get turned into acetyl-CoA. And some amino acids, the carbon skeleton can get turned into one of the intermediates of the Krebs cycle, of the citric acid cycle. So energy ultimately can come from all of that, because if it's part of the Krebs cycle, then you can get energy from it. If it's acetyl-CoA, you can get energy from it, energy meaning ATP. Okay, so this is what happens to the amino acid pool. The next thing on your what you need to know list talks about the 2 main reactions I want you guys to know in this chapter, the concept of transamination and the concept of deamination. Deamination deals with the urea cycle. So I'll deal with that in the next video, and then we will be all set. Okay.